we talked about a lot about gravity loads, and I think in structural design, everyone understands what a gravity load is, right? It's pretty logical. The weight all the way up on the roof needs to find its way down to the foundations. So similarly, wind loading, I think, makes logical sense to most of our owners. But one element that is difficult for many to understand is earthquake design and how a building keeps from falling over. Many people might have heard the term shear walls, but not really understand what it is. Would you explain why it's important and the different ways we can build this lateral design into a home?
To differentiate, think of a gravity design as you're standing and you have your arms out and people start loading books on you and you're just holding them. At some point, your arms are going to give out or your legs are going to give out. You'll sort of fall down. That's gravity design, too much weight.
Yep.
Lateral design is when you're being knocked over. So a wind design is say you're just standing, and somebody walks up to you and kind of shoves you. That's
Hmm.
wind design, is trying to keep the building from falling over. Earthquake design is if imagine you're standing, but you're standing on a skateboard and somebody walked up to you and tried to kick the skateboard out from under you.
Hmm.
That's what earthquake design is. During an earthquake, the ground is actually moving and can move a lot.
Yeah.
There's a very interesting video that was just recorded 3 weeks ago of the first known video we have of a visible seismic fault rupture that
Hmm.
happened in Burma. It was caught on a construction cam right in the middle of a 7 magnitude earthquake, and you can see the actual fault line rip and move over several feet.
Yeah.
It was big and huge, very interesting. Try and find that. But the ground is moving under you and the building is attached to it. So the building base tries to move and it brings the rest of the building over with it.
Right.
So it's just a load hitting you from the side. And even though the earthquake and wind, the way the force is applied is different, we actually design them in the same manner, except in earthquake. Like we use the same systems. But earthquake has higher and more stringent requirements, and we do design this thing called for ductility, but that's a different, more technical conversation.
Right. Yeah.
But essentially, we design these systems to keep things from falling over. So if you've ever looked at a building and seen steel pipes going like in triangles and things like
Hmm.
that, that's called a braced frame. That's one way of dealing with trying to fall over. You can think of you standing up straight with your legs straight, or you standing up with your legs splayed out like this so
Hmm.
that you can't be pushed over from side to side. That's a brace. A shear wall is a lateral system where the sheathing uh it tries to it's basically acting like a skinny uh very deep beam set on its side. So beams are usually oriented this way, or this is the
Okay.
top, this is
Yep.
the bottom. The shear wall is basically turned this way, and you're trying to bend that wall like this. But
Hmm.
because the shear wall is so long, even though it's so skinny, it's just that plywood, because
Right.
it's long because of geometry and physics, that length, the depth of that makes it really, really stiff. So it's called a shear wall because the entire building is trying to shear it over like this, but its own inherent structural stiffness is keeping it from moving over like that. So these lateral systems are wildly important because they stabilize a building from falling over, because inherently squares, the way we build buildings, vertical columns,
Yeah.
horizontal beams, are an inherently unstable shape geometrically. But triangles, that's why you see so many trusses with triangles,
Hmm.
are inherently stable. So we have to do a lot to make sure that these squares, that like, if you imagine making a shape out of like squares with sticks or straws or whatever, you can actually deform that and keep all the ends connected,
Yes.
but it's
Collapse it into a diamond very easily.
exactly, that's what we mean by geometric instability. But a triangle, you cannot do that without changing
Right.
the lengths. So we have to stiffen up all these square shapes, which is all our
Hmm.
buildings. And those lateral systems are the things that do it and keep it from falling over. You can find plenty of buildings under construction videos of buildings under construction on YouTube or whatever. that weren't finished and the lateral systems weren't finished and something happened and the entire thing just plunk, just falls
Yeah.
over easy. And
Yeah, because they haven't
that's the
installed the
important.
sheathing yet, so none of the shear value is there, and so it doesn't take very much to push them over.
Exactly, exactly. And so
Okay.
the different systems in higher end homes, we use a lot of moment frames, which are steel frames, which are light and airy, as opposed to a bearing wall, which you need the entire structural wall to do its job.
Yeah.
Um, and moment
Um,
frames are the shapes of squares, but they're
mhm.
they're very expensive because they're made of steel.
Yes. Yeah.
So,
Not just made of steel, but the point of the moment frame is you have this square shape, but there's nothing lateral inside of it.
mhm,
Right. And so you gain the lateral value by having the connections at the corners be extremely strong. Right. And
very,
so what other structural engineers have told me is that's expensive, A, because it's difficult for you to design, takes a lot of your time, and B, it's pretty heavy steel.
yeah.
Right.
And depending where in the US you are and how strong the earthquake is. When I mentioned that ductility, the minimum requirements, there are three levels of moment frames. We got the what we call the ordinary, intermediate, and special.
Hmm.
And the higher the load requirements or the higher the weights and things like that, it just becomes more and more expensive just based on the basic level of design that you have to do. So moment frames, yeah, they're difficult to design and lots of steel, big steel.
Yeah. So for the question of efficiency, it's best to create a design that avoids the use of moment frames. But there may be times where an owner decides, hey, this is somewhere that I do want to spend money. And that segues really nicely into our next question. It's very popular to have very large windows or operable walls, sometimes spanning 30 feet or even more. We account for this in design through long span beams with strict deflection requirements. Would you talk about what deflection is and the impact of a long span?
Yeah, absolutely. So, um, I'm gonna I'm gonna answer this in a slightly roundabout way, but then kind of hone in on it.
Okay.
So, as a structural engineer, we design for two things, one called strength, one called serviceability. So, strength design is that we design an element. An element is a beam or a column, just one piece of a building.
Hmm.
One element to do a job without breaking or bending, like yielding. I mean, like
Yeah.
bending to the point where it can no longer return to its original shape.
Right.
That's yielding. And that's called strength design, that this thing is strong enough to keep doing the job we need it to do. Then next we have service design, is this is when we're using it, are people comfortable still using it? Are people okay with this? Or is it doing something, it's not breaking, but it's doing something that we don't want it to. And here's an example of that. A diving board is perfectly strong and does its job every day but when you're walking on it, it is very bouncy, it is very springy, but that's the
Yeah.
job it's meant to do.
Hmm.
You do not want that in your floor in your home.
Right.
Even though it's strong enough, it's not breaking, it's not making you feel comfortable and at home. You're
Hmm.
feeling vibrations, you're feeling, so that's serviceability. Now, deflection is a serviceability design consideration. We consider deflection for the floor joist you walk on because too much deflection means it's too springy and you'll feel it, or it'll have sagging or things like that. In the case of windows, too much deflection means, or sliding doors, means you can't open the window or use the sliding door.
Right.
It's deforming it or shaping it too much. So if you can't use the thing, it's a failure because
Hmm.
building something that nobody can use, it just sits there. That's not the intended function of the building. It's designed to be used. So serviceability is very important. Now, the reason why it's important for Windows, I just said you can't open it or use it.
Right.
Now,
And you
the
might not be able to really see that difference, like
right,
particularly over a long span, if it's dipping by, a half an inch or over 30 feet or something in the middle, um, or maybe it's just a quarter inch. You can't really see it, but that's enough to bind the door so you can't move it.
right. Um, Now, as far as the impact of a long span, I do have to get a little bit mathy here, just a little bit.
Okay.
So we have polynomials. That's like when you got 1 plus 2x plus 3x squared plus 4x cubed plus 8x to the fourth. It's when we're stringing together
Yeah.
x to some power, right?
Sounds familiar from high school math a long time ago.
Exactly. So the strength design uses a first and a second order polynomial. Shear is when a beam or a column wants to cut like this. That's why we call it shearing.
Yep.
Moment design is when something bends, and that's a second order function. The third order function is angular rotation, and the fourth order function is a fourth order is deflection. That is the actual physical shape that an object will take when subjected to load.
Okay.
So, as a fourth order, if I double the span of a beam and want it to behave exactly the same way, that means I'm doubling the span by 2, so that's 2 raised to the power of 4, which is 16. Meaning, if I have an 8-foot window versus a 16-foot window, the
Hmm.
16-foot window, because it's twice as long as the 8-foot, the header over it, has to be 16 times stronger
Okay.
to do the same job.
I think that's a really important metric, actually. Let's just say that again. So when we double the span over that window, it doesn't have to be twice as strong. It has to be 16 times as strong.
16 times to do the same job.
Okay.
So long spans, your prices are you're going from 3 foot. A header is usually what, 2 2x8s.
Yep. Very small.
6 to 9 feet, depending on the loads above them. You might still be in dimensional numbers like 3 2x12s, or you might be going to LVLs.
Hmm.
12 feet, if reasonable loads, you still might be in LVL, but if you're in high snow load or a lot of roof load coming into it, you get to 18 feet, you're looking at steel. And
Yeah.
then 30 feet, you're looking at big
Yeah.
steel.
Big,
And
big steel.
and it's important that steel doesn't just go down, it goes out. Once you get past about 18 inches, I think an 18 by 40 is the last beam that will actually fit inside a 2x6 wall. Anything bigger than that, the flanges of the steel shapes start getting wider and wider and wider, and you can no longer
Yeah.
fit them inside a wall.
Right. And there are things we can do to hide that. So as an example of this occurring on one of the homes I was working on, we had, I think it was about a 25-foot span, very heavy snow loads, and this was at the bottom level. So there were two levels above, right, with their roof loads. And it was an operable wall system, all glass. And so that beam, I think it was 33 inches deep steel beam.
Toy.
So like that's the kind of steel that I remember seeing on the hospital project I was working on and did not expect to see that on a home project. But when we're asking for these operable walls in snow country, that's what we have to do.
The building I'm working on right now, one of the houses, is up on at the top of Powder Mountain. Like basically you
Hmm.
get off a lift and hey, there's somebody's ski house right there.
Yep.
Um, the design snow loads for the roof are 200 pounds per square foot. That's high. And you'll see that in Utah above about 7,000 feet, you start seeing really high snow loads.
Hmm. Yeah. Those snow loads have a really outsized impact on the overall system of the home. I've had some owners who come to me and they might be from Tucson or Los Angeles, and they want a very thin roof profile. And that's very difficult to accomplish when you have to account for 200 pounds per square foot of snow on that roof, because just the structure of the roof gets pretty beefy by itself.
Yeah, for sure. I mean, it's not uncommon to see 16-inch deep joists or trusses
Yeah.
that high.
Yeah. Okay, perfect. So I just wanted to touch on one more thing on deflection. So with these operable walls, I think that the deflection criteria that we had for this particular door was an eighth of an inch. And the beam above, the standard design for the beam was quarter-inch deflection. So can you talk about what those values mean and the impact that moving from a quarter to an eighth could have on the size of the beam overhead?
Moving from a quarter to an eighth. Sorry, I'm trying to do some mental math here.
Hmm.
5 times WL squared. I think that is actually might be a linear increase. So going from a quarter to an eighth, that would just double the size. It's not as sensitive as span. If you're just looking at the hard deflection limit,
Yeah.
since you're making it a function of the actual deflection itself, you would just need to, yeah, you would just have to, EI doesn't have any exponents. So it'd just be about, yeah, twice as big,
Okay.
yeah, essentially.
All right. So moving from a quarter inch deflection to an eighth inch deflection means the beam overhead is now twice as heavy,
Exactly. Or, well, it has to be twice as
approximately.
stiff.
Yeah.
But if you're maintaining the same depth, yeah, it's probably going to be about twice as heavy.
Okay. What are some common misconceptions owners or architects can have about what is possible or realistic?
So the first thing is, I get this all the time,
Hmm.
is, hey, look, I know you're still designing, but look, we really want to get the foundation in the ground. Can you give us the foundations? No, that is literally the last thing we
Yep.
design. Because we do design from the top down because gravity collects load as it goes down.
Hmm.
So that's one of the big ones. You want to get the foundation in the ground and have something to get started on, but that is literally the last thing, and I can't accommodate that. And the
Hmm.
foundation is the most important thing to hold it, make sure the building holds its shape, that it doesn't settle too much.
Right.
We don't see differential settlement. So you can't just wing that part of it. It has to be strong enough. Or if you do want it estimated, just you have to really, really over design and say, hey, this is way over designed. It's going to be way, way expensive, but that's what you asked for.
Yeah.
Another,
I've had projects in the past where they wanted to get foundations in while we're still designing other things. It's called a fast track project. It always ends up being very expensive and usually ends up taking just as long, if not longer.
yeah. So I know it sucks for the construction timetable, but it's the last thing engineered. Um,
Yeah.
Another is that cantilevers are difficult for so many reasons. And sort of like that deflection thing, cantilevers don't linearly increase complexity. They do it like by an order of magnitude, you know.
Okay.
And if you get beyond 4 feet of cantilever, you're into a really weird territory of you're having deflection issues, like the floor wants to act like, again, a diving board. It's very
Hmm.
springy, so it has to be super stiff. Um, if you get a lot of point loads at the end of that cantilever, like if the cantilever is supporting a wall above, that's a big deal.
Yes.
Um, if the cantilever is supporting a lateral system, like the shear walls we were talking about, or a brace frame or a moment frame, that makes it so bonkers complex. So cantilevers really introduce a huge amount of complexity that are, for the most part, doable, but it's not just a linear increase in cost. It's going to represent a huge cost increase that you got to be just very aware of.
And I think what you're talking about is mostly having to do with how much load is on that cantilever, right? So let's say the cantilever is just like a deck. If we refer to Frank Lloyd Wright's Falling Water, for instance, there are these very long concrete cantilevers. How did he do that to make it structurally stable, even now, 100 years later?
If you look at them, some of them are tapered down so that you have increasing depth, so you have increasing stiffness as
As you
it,
go back toward the home, so it's
yeah,
thin on the very outside edge.
yeah, and you can
So it's
see
it's, it's
that
a triangle shape almost.
essentially. So it
Okay.
gets stiffer and stiffer and stiffer. You can see that in a lot of modern cantilevers. That's one way to deal with it. Another is like you can reinforce concrete heavily, but I mean, I am willing to bet that there's a bonkers amount of rebar in
Hmm.
those to hold those decks up. Also, it's probably, falling water is not designed in a high snow load location. Uh,
Hmm.
there are other things to consider, atmospherics. That's actually another thing I want to bring up.
Okay.
This sort of goes back to site selection, is understanding that that what works for Florida isn't going to work for Maine, isn't going to work for Minnesota, isn't going to work for Salt Lake, isn't going to
Yes.
work for LA. Florida has hurricanes, no snow. Maine has a lot of snow, sometimes nor'easters. Minnesota has a ton of snow. Salt Lake has some snow, but we have earthquakes at the same time, and in the high
Hmm.
mountains we have snow and earthquakes.
Yep.
LA has bonkers earthquakes. Everywhere is different, so you can't just expect that just because a building works here doesn't mean it's going to work over here.
Yeah. And when it
Um,
comes to the structural package, that could mean, if someone has built a custom home in Florida, then they come to Utah and they want to build, a similar size custom home, it could be significantly more expensive because of the heavier structure.
right, right. Let me see. What other misconceptions about what's possible? Oh, long spans, again, doable, but there's that deflection issue. So if you're going from like a normal span in a house is maybe 16 to 18 feet.
Hmm.
When you start getting into open floor concepts and all that sort of stuff, you're looking at 30, 40 feet spans. I mean, you're big beams. Big
Yeah.
beams also means big columns, means big footings. So
Well, and then beams can become trusses, right, which are lighter and quite strong, and that you can get some longer spans that way too.
yeah, yeah. And you're still dealing with the reactions at the end though, and
Hmm.
so foundational elements and stuff. But there are ways to deal with it. It's just important that you calibrate your expectations realistically for these
Yeah.
long spans or open floors or cantilevers and things like that. I mean, I often say that you can do anything as long as you have the willpower and a good enough budget.
Yeah.
That's the sticking point, that second one. So it's just being
Right.
aware that these choices, again, while doable, will affect your budget.
Yep. Yeah, it's all compromises. If you want to spend money over here, you can't spend it over here. So,
Right.
okay, perfect. You mentioned soils there. We talked about soils earlier. I do want to come back to it just for one additional point having to do with the soils report. So, what do you look for in the soils report, and what different directions can different types of soils take you in regards to foundation design?
Okay, sure. So what we look for in the soils report is first off, if there are no hazards. That's generally a separate report, but there will probably already be a flag on the site by the building department or the USGS or something that says this is a hazardous site. Like if you're building on a fault, I mean, there's so much you have to do. But if there are no hazards, then I start moving on to soil types, and this is an entire branch of engineering.
Hmm.
Uh, as a structural engineer, I just look at what they give me and follow their recommendations generally because it's a very this is an entire profession, understanding the earth and soils. But
Hmm.
there are generally two different types of soils, most generally, things that react to water and things that don't react to water.
And is that like a sandy soil versus a clay soil?
Exactly.
Hmm.
Clay is it reacts with water. It can expand, it can contract, it can get sticky, it can fall apart, it can do all sorts of stuff.
Yep.
Gravel or just dry sand, you pour water over it, it's just dry sand still. Like there
It
might be
just
a
filters
little,
through pretty quickly.
yeah, exactly. So what we want to see is sandy soil generally, because it has reliable bearing pressures. It doesn't react in unreliable ways to water. Oh, excuse me. Um, but we're looking for the water table as well, as far as design characteristics now.
Hmm.
So first the soil types, now design characteristics. We want to look at where the water table is, because that will affect our foundation design, and builders. Like, yeah, we can build with a high water table, but there might be buoyancy issues,
Hmm.
different strength things, stuff like that. But then actually building it is a pain because they've got to de-water while building. So the water table affects us. Expansive soils. So if we see clays and silts and stuff like that, we have to design for changes in changes in how thick a soil layer is. It can
Uh-huh.
heave, it can collapse, it can do all sorts of weird things. And then we're looking at bearing pressure, how much the soil, this is the biggest parameter that they give us. How much weight, how much pressure can the soil take before failing in some way? And that's the bearing pressure value. That's the biggest one we design off, but all of these things are important.
Yeah.
Then with those parameters, we the based on what they find and also slope of the site, I guess I forgot to mention.
Hmm.
Um, the geotechnical engineer will give you options in the report to say, this is an option, this is an option, this is an option, this is an option. Most traditional is what we call shallow foundations. These are foundations, traditional things that you would see like the concrete wall with strip footings. And they're called shallow because they generally max out at about 5 feet deep at
Hmm.
most. You just care about getting below the frost line.
Right.
And then we've got deeper foundations, which are piles, um, which are helical piers or driven piles or auger cast in place, whatever. Those are um, those are for used. Those are used when your soil, the topsoil layers are complete, utterly useless garbage. I have had to put houses on these
Hmm.
before for extremely heavy loads. Like basically every bridge, every skyscraper is put on piles because they're very long and they go deep and they can hold a lot of weight.
Yeah.
Um,
So do piles in all cases go down to bedrock? Is that the point?
no, no, no.
Not
Um,
not always.
a, a lot of them will and can, but you get a lot of strength out of something called skin friction. That is because the earth is pushing in, and it's sort of like you having a book and putting your hands on either side of the book, hold it up to keep it
Uh-huh.
from falling. The
Right.
piles, the earth is actually pushing on these and creating a lot of skin friction, and you
Okay.
can support a lot of weight on a like a 50-foot pile. You can support maybe 200 kips, 200,000 pounds. Like
Right.
it depends on the soils, but that's one of the parameters. If they do make a recommendation for piles, they give us various parameters called like skin friction, any down drag friction values and things like that. But that will all be in the report as well. And then you work with the owner to talk about what are your expectations for settlement and differential settlement, um, and how do you want to approach this. Sometimes you might just want to get rid, if there's a thin layer of bad soil up top that you can just get rid of and replace, that might be an option as well. So it's just
Yeah. Sometimes expensive, but maybe
yeah, yeah, because
necessary.
you have to dispose of that unusable soil somehow. And that's expensive
Yeah.
too, because you have to pay to put it in a construction landfill.
Yeah. If your site's large enough, sometimes you can dump on site in certain places. But very specific situations for all of that, all those questions.
Right. So they'll generally give us options in the report, and then we work with the owner and the architect to try and figure out like what their goals are, how much can they spend, want to spend, and what kind of foundation they want to look for.
Okay. Um, I think that's just another reminder to all the owners. Get the soils report and review it before you buy your site,
Yeah,
right? You don't want to be surprised to find out that you have to do, piles and bring in a bunch of engineered soils that's going to cost you X number of dollars that but you didn't have account for in your budget. And then all of a sudden that could end your project depending on how tight the budget is. So
right.
we move on to something maybe a bit more lighthearted. Do you have a memorable story of a custom home design that was challenging and required some creative solutions?
Yeah, we had one from an engineering standpoint. I didn't get to make a lot of these choices. I basically sort of made it work and helped the architect refine it.
Hmm.
But we had a site that was on the side of a mountain, so heavy slopes,
Yep.
and then also it was split in half by a um, drainage easement that we couldn't build anything off, like the site was. So what we came up with was essentially, and it went diagonally through the site. So at the roadway, in sort of into two triangles. So at the kind of the triangle
Hmm.
at the roadway, we built half the structure, like half the usable space that the client wanted. And then on the other half, we built the other portion, the rooms and things that they wanted in their home. So we had
Okay.
a garage and an office working space and a small deck over on this side. Then we built a bridge to the other side. And the house, because it was on such a steep hill, built this entire thing on stilts, essentially.
Hmm.
Um, just really big steel columns and some um, they weren't pile foundations, but they were kind of deeper just to accommodate the slope and make sure it was still stable. And we built the entire structure on like that. And the challenges were, so in an earthquake, you can't have the the one building drift over, like the building being hit by the earthquake. Stilts are a lot less stiff than shear walls, like
Yep.
the garage. So the
Did they
building,
have some lateral bracing in them, or was it just vertical stilts?
those vertical stilts, and I had a couple of, I think I had two bays of two on each, actually one on each side. So there was some lateral bracing, but we had to calibrate the braces to make sure that the buildings, the shear wall building, drifted over as much as the stilt building, because if they moved too much in with respect to each other, the bridge would get stretched, distorted, and could possibly break. So we had to try and
Yeah.
make them respond the same using different systems. And
So
that's
I just want to clarify. This was not on a fault line. It was
no,
over just a drainage channel. So there's really no expectation that the homes would move or the two parts would move separately from each other.
right. It's just that
They should move together if there's an earthquake.
well, yeah, but think about like if you've got like pendulums, how they have different natural times they want to
Hmm.
swing at, which is a function of how much weight is on there and how long and stiff long the string is or whatever.
Yep.
Buildings do that too. So two identically high buildings made of different stuff will actually wiggle differently in the same earthquake.
Okay. Yeah. Fair.
So the stiffer the building, it'll wiggle quicker and not as much. It'll be vibrating really, really quickly, while a skyscraper in the same earthquake will sway back and forth in this long, long way. We call that the building's natural period.
Hmm.
And so we had to try and make them have the same period so that the bridge wouldn't get destroyed in an event. And that was
Oh,
challenging and a lot of
really
fun.
fun design.
And it was pretty too. It came out looking really pretty.
It sounds very interesting. That's what I'd like to see. Okay. Anything else you'd like to add about the importance of working with a structural engineer in home design? We've covered a lot of topics today.
Yeah, I mean, other than to say it's required by law in most places,
Hmm.
um, it's best to have a good relationship with a good relationship between all of the parties. Good communication between them working together towards your goal is important. Like oftentimes in our profession, AEC, I've said that before, that's architecture, engineering, contracting, are because we're working toward different goals. I want safety. The architect is designing the house for you so you can use it properly and also be fit your aesthetic need, that it fits your service needs, whatever you need. And then the builder wants to build things cheap. So we're all approaching the same problem
Hmm.
from three different points of view. And quite often, that relationship, if we're not working together, becomes adversarial.
Yeah.
So if you work with the structural engineer and the architect and the builder all together, um, it'll make everything go that much smoother. You'll be more informed, and it is your house. You have every right to know who's going to be working on it, um, and involved in the design. So that's yeah, it'll be a smoother project for you if you work directly with everybody involved.
Yeah. Good advice to owners to form good relationships with everyone and get a really well-functioning team right up front. It's one of the most important things you can do.
Yeah.
Okay. That is our time. Chris, thank you for joining the conversation around the drafting table today to provide your thoughts on structural engineering. And until next time, get in touch with Oxford Architects so we can dream together.